observable annotated samples more efficiently. This architecture consists of contracting path to caption context and semantic expanding path that enables precise localization. We show that such a network can be trained end-to-end from very few images and outperforms the prior best method, a sliding window convolution network. It outperforms on the ISBI challenge for segmentation of neural structures in electron microscopics, and uses the same network trained on transmitted light microscopy images, phase contrast, and BIC. And we won the ISBI cell tracking challenge in 2015 in these categories by a large margin. Moreover, this network is fast. Segmentation of 512 image takes less than a second. On a recent GPU, the full implementation is based on Caffe and is trained, and then trained networks are available at their website. This is the older one, but this is paramount for how convolutional networks work. Okay.
Yeah, so this is just literally a bunch of actually, we'll get into the image later.
Okay.
That's a pretty good way of actually demonstrating how the model looks. It's literally just a bunch of mathematical operations just stacked up on top of each other. And you see the shapes there, 128, 282, 280. Those are literally the size of the blocks. So that's this is pretty, I haven't seen this type of visualization for the model architecture, but it's pretty good. Yeah, so you see there's convolutions, 3x3 ReLU, copy and crop, max pull up, convolution. Yeah, those are literally just mathematical operations. This is literally Lego blocks. You're literally playing Lego blocks with a bunch of mathematical operations that transform an input data type into a statistical model. Basically, all of machine learning can be summarized with these following words. There's two components. You have the number of bits, which is the input data, and then you have the number of bits that you're modeling. So how are you modeling these bits? This is what the model accomplishes. So if you could understand these two things, you can understand all of machine learning. You just have a number of bits, which in this case, it's the input image tile all the way on the left. And then the modeling is all these mathematical operations that just do things to try and attempt to get a model that can understand the bits. This is all of machine learning.
Okay. Introduction. In the last 2 years, deep convolutional networks have outperformed the state-of-the-art in many visual recognition tasks. While convolutional networks have already existed for a long time, their success was limited due to the size of the available training sets and the size of the considered networks. The breakthrough by Kavinsky was due to the supervised training of large networks with 8 layers and millions of parameters on the ImageNet dataset, with 1 million training images. Since then, even larger and deeper networks have been trained. The typical use of the convolutional networks is in classification tasks, where the output to an image is a single class label. However, in many visual tasks, especially in biomedical image processing, the desired output should include localization and a class label, and is supposed to be assigned to each pixel. Moreover, thousands of training images are usually beyond reach in medical tasks. Once Kerrison trained the network in a sliding window setup to predict the class label of each pixel by providing a local region patch around that pixel. Okay, so here's the Unet architecture. That's the 32 pixels by 32 at the lowest resolution, and then each blue box corresponds to the channel, the multi-channel feature map. And then the number of channels is noted on the top box.
So,
and the channels here would just be the number of like convolutions, the image masks, essentially.
yeah, so I might be mistaken, but the numbers 284, 280, 572, 570. I don't know if this is the size of the input image or if this is the size of the convolutional net. What do you think it is?
I would guess size the convolution.
Yeah, that's probably what it is. Then as we go down, we have so the first 10 plus layers. Actually, no, you have two. The beginning are two convolutional 3x3. Yeah, so if you look at them, you see the 2x2 in the bottom part, and then at the top you see 164, 64. You see? So that's 3x3. That's what they mean by 3x3. And then as we go down, we see the max pool. So you remember what the max pool does? It literally shortens the tensor. It takes a max out of each stride or quadrant. And then this is why it gets smaller. You see it got smaller?
Yeah.
So then so like in the beginning, there's the two first convolutions. Then it goes down using max pull. Then you do two more convolutions that are 282 to the second power, and you have 128. Then you take the max pull of that, and then you do two more convolutions, and then you take the max pull of that, and then you do two more convolutions, and then you do that even more, and then you're like, you see how the input image, look at how big the input image is, then look at how small it is at the bottom.
This just compresses the images.
So yeah, basically, yeah. So it's basically like compressing the image into the max pull compresses the image. How can we explain convolutions, Evelyn? A 3x3 convolution. Oh, you do?
They're just
Can you look up
a piece of an image.
Yeah, can you look up convolution 3x3 on PyTorch?
Yeah.
That's China, I think. The background was nice. All right. PyTorch.
Convolution, a filter, which is a shape or tricks. It is applied in a sliding window to detect it.
Yeah, go to the documentation. This isn't the documentation. This is a discussion. Just look up PyTorch. Yeah. Actually, just do do that. So this is one dimension. They're using 3-dimension. So it's different. Yeah. Maybe it might not be this. No. Can you go back to the paper for a sec?
Yeah.
So 3, yeah, I don't. Is that one-dimensional convolution, Evelyn, or is that 3-dimensional? It might not. It might be one-dimensional.
So they likely apply by 3x2 solution those layers of different layers in the images, as they will be split by color. That is, there'll be a red layer, blue layer. But those layers will be processed with the same size of solutions separately. And the end result will be passed through the next, again, split by color down. Resize happens when it is passed to the next.
So why this for compressing and resizing images?
Yeah, this is a 2-dimensional convolution. What was that, Zach?
So I'm just wondering. I guess I don't quite get the need or why this method, because there's other methods for like compressing
Like what?
images.
What methods?
Well, like just getting them lower resolution or just resizing them. Is this different from that? I don't know. Like,
No, not.
right.
Yeah,
So
it's the same.
okay. So this is.
Look at how long the input image is. Look at how long it is. You're just compressing that into that little box at the bottom. You understand?
Well, it's saying here that this is the output.
Yeah. So, you're trying to get the model to learn all the features of the image. So you need to compress this in some space. That is why we're doing this. Because if you just put the image as it is, it's not going to learn anything. It needs to learn.
Is it compressing the tensor then?
Yes, that's what it's doing. So when you see in the beginning, this is a tensor. This is not an image. This is a tensor of an image.
Let's see.
So at the bottom, it gets max pulled, then then double convolution, then up convolution, which adds the white spot, basically adds information. So that like up convolution 2x2, then double convolution, then up convolution 2x2. You see it adds the white space, then again, and then so like the up convolution adds space or adds information. And at the top, you can see like there's a white mark at the beginning after the up convolution, and then there's a 3x3 convolution, and then the final convolution 1x1, which gets the output of 388s, and 2. Do you have any questions, Zach?
Yeah, let me just try to. Okay, so
They're just applying these convolutions.
And it just copies and crops it. And then those are also sent through convolutions. And then, okay. Yeah.
If you want to learn more what a convolution is, just check out the documentation.
Yeah. No, I understand convolutions.
What's
okay, so just how well this is repressing. I guess I was just getting tripped up with like the actual flow of this. trying to understand
How does it
the
learn?
actual flow of all of this. I know it's like it's compressing the tensor, but like why does it need to copy and crop this end and then also feed back in the okay, so this is just making it smaller. This is just dialing in on a piece of the image.
So that is
Or
so
yeah, I know it's using max pole and
the max pole compresses or
Yeah.
takes the maximum of each segment.
yeah.
So it's just compressing the image by making it smaller.
Yeah, no, I understand that. First, this network can localize. Secondly, the training data is, in terms of patches, is much smaller than the number of training images, and then resulting in the network that won the EM segmentation challenge at ISBI 2012 for live web. Obviously, the strategy in Pearson has two drawbacks. First, it is quite slow because the network must be run separately for each patch, and there is a lot of redundancy due to the overlapping patches. Secondly, there's a trade-off between the localization accuracy and the use of context. Larger patches require more max pooling layers that reduce the localization accuracy, while smaller patches allow the network to see only a little context. More recent approaches proposed a classifier output that takes into account the features from multiple layers. Good localization and the use of context are possible at the same time. In this paper, we build on a more elegant architecture, the so-called fully convolutional network. We modify and extend this architecture textures such that it works with very few training images and yields only precise simulations. The main idea in design is to supplement a usual contracting network by successive layers, where pooling operators can be replaced by unsampling operators. Hence, these layers increase the resolution of the output in order to localize high-resolution features from the contracting path and are combined with the unsampled output. And a successful convolution layer can then learn to assemble more precise outputs based on the information. Here is the overlapping strategy for seamless segmentation of arbitrary images. Your segmentation of the neural structures in EM stacks predict the segmentation in the yellow area and requires image data within the blue area as the input. Missing input data is extrapolated by mirroring. One important modification in our architecture is that it is sampling part that we have as a large number of feature channels, which allows the network to propagate context information to higher resolution layers. As a consequence, the expansive path is more or less symmetric to the contracting path and yields a U-shaped architecture. The network does not have any fully connected layers and only uses the valid part of each convolution. The segmentation map only contains pixels for which full context is available in the input image. This strategy allows the seamless segmentation of arbitrarily large images by an overlap tile strategy. To predict the pixels in the border region of the image, the missing context is extrapolated by mirroring the input image. This tiling strategy is important to apply the network to the large images, since otherwise the resolution would be limited by the GPU memory. As for our tests, there is very little training data available. And we use excessive data augmentation by applying elastic deformations to the available training images. This allows the network to learn variance, such deformations. Without that, the need to see these transformations in the annotated image corpus. Without the need to see the image transformations in the annotated image corpus. This is particularly important in biometric segmentation since the deformation used to be the most common variation in a tissue, and realistic deformations can be simulated efficiently. The value of data augmentation for learning variance has been shown in Tarowski in the scope of unsupervised feature trait learning. Another challenge in many cell segmentation tasks is the separation of touching objects of the same class. To this end, we propose the use of a weighted loss where we separate background labels between the touching cells and obtain a large weight in the loss function. The resulting network is executable in various biometric segmentation problems. In this paper, we show results of segmentation neural structures in EM stacks as their own competition, where we outperform the network of Pearson, and furthermore, we show the results for the cell segmentation in light microscopy images from these ISBI cell tracking challenge. And here we run the network architecture. Network architecture in Figure 1 consists of contracting path on the left side and expansive path on the right. The contracting path follows the typical architecture of convolution networks, and it consists of repeated application of 2/3 convolutions, uncounted convolutions, and is followed by a rectifier linear unit, RELU. And the 2x2 max pooling operation with a stride of 2 for downsampling. At each downsampling step, double the number of feature channels, and every step in the expansive path consists of unsampling of the feature map followed by a 2x2 convolution and convolution that halves the number of feature channels and concatenates with the corresponding cropped feature map from the contracting path in 2 3x3 convolutions, each followed by RLU. The cropping is necessary due to the loss of border pixels in every convolution, and the layer of a 1x1 convolution is used to map each 64 component feature vector to the desired number of classes. In the total network has 23 convolution layers. To allow a seamless tiling of the output segmentation map, it is important to select the input tile size such that all 2x2 max pooling operations are applied to a layer with an even X and Y size. Framing. The input images and their corresponding segmentation maps are used to train the network with the associated gradient descent implementation. Due to the unpadded convolutions, the output image is smaller than the input by a constant border width. To minimize the overhead and make maximum use of the GPU power, we favor large input tiles over large batch size and hence reduce the batch to a single image. Accordingly, we use high momentum and such that the large number of the previous training cycles to determine the update in the current optimization step. The energy function is computed by pixelized softmax over the final feature map, combined with the cross entropy loss function. Softmax is defined as pkx equals the exponent k. So we have pk, so the pixelized. Yeah, so we get the pixelized k here would be. Okay. Where AK of X denotes the activation feature in the channel, K is the pixel position, X is a part of omega, with omega
Omega is a part of Z. Actually, can you look that
how
up?
did these?
Look up set theory notation.
Oh, this is a subset. This would be.
Look up
This would be a
set theory. Look up set theory notation, and then we could see everything. So this is set theory. This is the theory of sets. So literally just sets of stuff. There's a whole like notation vocabulary for this. A lot of machine learning uses a lot of traditional. So you see, if you go up, you could see like, the n. So that n right there, that's what that means. Literally means they're together. Actually, go back. Go to the image. I want to find like a cheat sheet. Go back. Yeah, go to the image. Yeah, I'm trying to find a. Go to set theory notation. Go back. Oh, that's pretty good. So intersection means A and B are like intertwined, and then A and B are together in the beginning. Union. Then you have the proper subset, which is what the one that we're like the one that we're at now is proper subset. That's the fourth one. So the dictionaries implies a set. If you see a dictionaries at the top, that's a set. And then the psych, you see the circle with the line in the middle, that's a empty set. And the Z means integer numbers, C means complex numbers, R means real numbers, Q means Q like that, or like italic. Is that italic or just, I don't know how to say it. Q means rational numbers, N means natural, universal. And then some. So the A, like E, B, A, B, that means set membership. That means A is a part of B. So there's a set that is a part of a set. Look up, can you go to another one and see what proper subset means? You gotta find proper subset. Go back. Just find one.
Find one.
Proper subset.
Oh, in the images?
Yeah, just click on a random one. Click on the fifth one. No, yeah, the fifth one with the very bold. Yeah, no, yeah, that one. Yeah. Yeah, not good. Look up set theory visualization.
Oh.
Yeah. So it's literally just click on the first one. And not good. Yeah. Look up what is a proper subset of. Look up proper subset. proper subset. Yeah. Oh shit, this is too complicated. Fuck that. Damn.
All that proper subset means is that side of the relation is bigger than the.
So a proper subset is a set that contains some but not all of the members of another set. This is a bad page. No good. Yeah. All right, let's just go back. Do you understand what this means?
Yeah.
So it's a set that is.
Well, I'm not actually.
It's a set
It's just a
that
set of numbers.
Go to the paper. Go to the paper.
And just how they relate to each other.
So
whether they're a subset or they're part
omega
of the subset.
omega
or
is a
they're-
part of omega is a part of. See, X is a part of omega. The set of X is a part of omega. Omega is a proper subset of all. What was it? All integers. Or what was Z? I forgot what Z was. So omega is a part of Z, but it's not fully a part of Z. There's some things that are missing.
Yeah.
So Z is all integers or something. Look up Z set theory.
Okay.
Damn, bro, I forgot what this was. We were just talking about this. So Z is
You know that just denotes a set of integers.
what?
It's just a set of integers.
Yeah, so omega is a part of a set of integers. That's how you would read that.
Okay. K is the number of classes, and P of K passing X is the appropriate maximum function. The P of X is approximately 1. The K has maximum activation. A of K, which is the activation feature, then has, and the pixel position are approximately 0 for all other K, for all other channels. And then the class entropy then penalizes each position and deviates from the pixel layer, and the X and X for missing for using one. Okay.
So that is, so E equals the sum of W times, or W function of X multiply with the log of PL subset X applied to X. So that means the sum of the wx log whatever to, or actually look up sigma notation. You just find an image. So yeah, go to the third one. Yeah. So final index. Evelyn, correct me if I'm wrong, but the final index implies the like maximum. Or like, could you
Final index means the last element
the last number?
that will the last row and column. And so this is unrolled, a single row, and so it will be the final value.
Okay.
And then what was the bottom one? Go back.
The sum will be from the initial part of the matrix by rows all the way through to the final value.
Huh. Do you understand this, Zach?
So when it passes E into this, the E is trying to be the final output from sigma. So we take the input, and that is
X is a part of omega.
a subset part of omega. Yeah. So X is X would be the just what we're solving.
X is the input tensor most of the time.
Oh,
unless
okay,
unless they explicitly say something that implies that it's not.
Okay.
Yeah.
Figure 3. Power cells are a glass reported with DIC, differential interface contrast, and microscopy. A is a raw image, B is an overlay of the ground truth segmentation, and the different colors indicate different instances of the hello cells, and the C is a generated mask, whereas the white, with the white and white foreground and black background, and D is a map of the pixelized weight to force the network to learn the border pixels.
So
okay.
let's take a look at the image. So halo cells are recorded with DIC, differential interference, contrast, microscopy. A is raw image. B overlay with ground truth segmentation. So this is, if you look up Unet implementation PyTorch GitHub. Look that up.
Unet implementation PyTorch.
Yeah, look up Unet PyTorch GitHub. I want to show you what the Unet actually does. Like, what is the actual output? Do the second one. Second one.
Oh.
So that right there is what the Unet does. It creates a mask. So Unet takes the mask of an image. That's scroll down.
Wait, so it's not compressing the image, or is
Go scroll in. scrolling, like go deeper. So this is what the Unet does. This is all those mathematical operations you saw. This is what it's learning. It is learning to take an input image and create an output mask. This is what Unet does. This is why it's used in diffusion models and for text to video, text to image. It takes the mask of the car, whatever the image is, and then we diffuse this process. Then we add noise, and then this is how we have diffusion models. But as you can see, it literally just takes an image and it learns to separate things in the image, and that is the whole purpose of a Unet. You understand?
Yeah.
So what you were saying, like, it's not actually compressing an image. Those are just like the tensor. You're compressing the tensor size to learn how to separate things inside of the image. But the image is not smaller. It's the same size. It's just learning how to separate things in the image. You understand?
Mm-hmm.
So
Yeah. Okay.
that's,
We compute the weight map for each ground truth segmentation to compensate the different frequencies of pixels for a certain class in the training data set. And we force the network to learn the small separation borders that we then introduce between touching cells. The separation border is computed using morphological operations. The weight map is then computed as the weight input tensor is equal to the weight computed input tensor plus the weight, operations times the exponent, and then that way times with the negative d, so d would be negative d of x, and then hold on, the weight, where the weight of c is equal to omega that we get from the real number, and it is a weight map to balance the classifications where d1, so that denotes the distance. D1 is a function that gets the omega from the real numbers, and then it denotes the distance to the borders of the nearest cell, and distance 2 function similar to the 1, and the distance to the borders of the nearest second cell. In our experiments, we set the initial weight to 10, and sigmoid is approximately 5 pixels. In deep networks with many convolution layers and different paths throughout the network, a good initialization of the weights is extremely important. Otherwise, parts of the network might give excessive activations, while other parts never contribute. Ideally, the initial weight should be adapted such that each feature map in the network has approximate unit variance for network with architecture, and alternating convolution and RLU layers. This can then be achieved by drawing the initial weights of the Gaussian distribution with the standard deviation of the square root of 2 divided by n, where n denotes the number of incoming nodes of one neuron. Example, for a 3x3 convolution in a 64 feature channel in the previous layer, n would equal 9/64. Data augmentation. Data augmentation is essential to teaching the network the desired variance and robustness properties. And only a few training samples are available. In our case, microscopic images, we primarily need to shift and rotation invariance as well as robustness to the forms in gray value variations, especially random elastic deformations of the training samples seem to be the key concept to train segmentation network with very few annotated images. We generate smooth deformations using random displacement vectors and of course 3x3 gradient. The displacements are sampled from the Gaussian distribution with 10 pixel standard deviation. Per pixel displacements are then computed using cubical interpolation. Dropout layers at the end of the contracting path perform further explicit data augmentation. Experiments. We demonstrate the application of Unet to 3 different segmentation tests. The first task is the segmentation of neural structures in an electron microscopic encodings. An example of the data set and our obtained segmentation is displayed in Figure 2. We provide the full result of the supplementary material, and the data set is provided by the EM Segmentation Challenge that was started at ISBI 2012 and is still open to new contributions. The training data is a set of 30 images, 512 by 512 for serial section transmission electron microscopic of the dystrophilia first instar lava ventral nerve cord. Each image comes with a corresponding fully annotated ground truth segmentation map for the cells in white and the membranes in black. The test site is publicly available. The evaluation can be obtained by sending predictive membrane proximity maps to the organizers. The evaluation is done by thresholding the map at 10 different levels of computation of the warping error, the range error, and the pixel. The Unet achieves without any further pre-processing the warping errors. It achieves a rounding error of 0.0382. This is significantly better than the sliding window convolution networks resulted by Garcian, and whose best submission had a warping error of 0.004 and the rounding error 0.5. In terms of round error can be only better performing. The only better performing algorithms on this dataset use highly data-specific pre-processing methods applied to the probability map. So here we have a table without ranking this, and then there's the result of the cell tracking challenge. A are the image on the data set, and then B is the segmentation result with the cyan mask with manual ground truth as the yellow borders, and C is the input image of thick data set. D is the segmentation in random numbers, and manual ground truths as the yellow borders. We also applied the Unet to cell segmentation tests in light microscopic images. This segmentation test is part of the ISBI cell tracking challenge in 2014 and 15. The first dataset, HC, contains glioblastoma nickel bells on a polypropylene substrate recorded by a phase contrast microscopy. It contains 35 particularly annotated training images where we achieve an average IOU intersection over union of 92%, which is significantly better than the second best algorithm, 83%. The second data set, Capella, which is celled with blackgrass with a different interface contrast. It contains 20% particularly annotated training images where we achieve an average IOU of 77%, which is significantly better than the second at 46. The Unet architecture achieves a good performance on very mild biomedical segmentation applications thanks to the data augmentation with elastic deformations. It only needs a few annotated images and it's very reasonable training time, it will be 10 hours time, and we provide a full Caffe-based implementation of trained networks, and we are sure that the new architecture can be applied easily to many more tasks.
That's it.
That's
Fucking
it.
10 out of 10 paper. Super short, super impactful. I mean, I can't possibly say how important this paper is to diffusion. It's literally in every diffusion model. Every single one. Like all of them. Every single one. It's really important. Really, really important. And understanding how it works is also much more important. I haven't fully understood how diffusion models work, but now I'm able to understand a little bit more. And basically, the Unet's purpose is to essentially just like provide. It creates the mask, like I said. It separates the image. It separates the core component of the image with the background. That's what it does. And so this is why it's critical to any image diffusion model. What did you learn, Zach?
Yeah. So I also don't know very much about diffusion models or any models for that matter, but I can see why this would be much more beneficial than like a sliding window convolution, because it's actually learning objects in an image rather than just pieces, piecing those pieces together.
Mm-hmm.
Yeah.
Yeah. I've made a simple, as you were reading, I made a simple implementation of this. I'll show you what it looks like in PyTorch. So here is the here is Unet. Here's the double convolution that you were seeing. So we initialize the channels. All the convolutions take in channels, which is how much you're gonna convolutionize the input tensor. So the first step is a two-dimensional convolution, then batch normalization, then ReLU, then 2D convolution the same, then batch norm with the out channels, and then a ReLU. And then a sequential, you just apply this to the X. And so this is just sequential. This is just like a sequential loop. So you're applying these operations one after the other. So we do that here. Then we have the down. Remember I was down sampling it, making it smaller? This is what that is. So first we have the max pool, which takes in the max pool of the input. And we're saying 2 for that. Then we have the double convolution. You remember? So we would do down.
Yeah.
We do 2 convolutions, then go down. Then 2 convolutions. So that's that. Then we have the up sampling. So we have a parameter here that says if it's bilinear, then we do up equals up sample with a scale factor of 2, and we align the corners. Then we have the convolution, which is the double convolution class that we made. In channels, out channels. In channels divided by 2. Then we have so then we have convolution transpose. So you remember what a transpose was? We have a matrix and we're flipping it. So if it's horizontal, we're going to make it vertical.
Okay.
That's what a transposes are really important. They just flip the matrix on its side some way. So if it's vertical, it'll be horizontal. If it's horizontal, it'll be vertical. Then we do double convolution. So here we do we upsample with the convolution with a conv transpose or the upsample. Then we take the derivative of y minus x1 size, then the derivative of x2 size minus x1 size. Then we pad it. How to explain padding? We pad this. Then we concatenate both of them. Then we return the convolution applied to the x. And then this is the final one, the final module. We take the convolution 2D and we apply that to the input image. So we only have a kernel size of 1 here. Then we have the Unet. We initialize some stuff. We initialize the parameters. So you see the down 64, 128. Then we'll go down 200, 128, 256, 256, 512. You see how it's going? Ding, ding,
Yeah.
ding, 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 ding. Okay. So then we have the fourth down. This is 512, which is the output of the last one. Then we put that to 1024 divided by the factor, which is 2. So we divide this by 2. Then we have the upsample, which is actually going down. So 1024, 512. 512, 256. 256, 128. 128, 64. Then we have the output convolution, 64. And so we're just initializing stuff there. Now it's when we do the nitty-gritty stuff. So first we apply the double convolution, then we do down, then we do down, then we do down. So remember the down contains the max pulling and the double convolutions. So keep that in mind. Now we have, we do that a couple times, then we have the up. Now we have the up 4 times, and then we apply the last convolution. And that's it. So if we try to run this, let me show you what it would look like. So let's see what the outputs look like. So this is the input tensor. Look at the values.
Okay.
Now look at the values when they're out.
Okay.
So they're all between 0. You see that? That's the first thing. So in the input tensor, look at them. They're kind of like all over the fucking place. -3, 2, like a bunch of shit. In the output, they're all between 0 and 1. You see?
Yeah, I see that.
So also, you see how it was smaller? Now it got bigger. So if we print the shape, we can do that by doing shape. So we see the shape. This is the dimensional tensor. So we have batch, height, width, and channels. So you see, we added in one more dimension.
Okay, so if the output is just a mask of the image objects, essentially,
Mm-hmm.
if I understand correctly, so it's just a mask of the image objects, then I guess that's why there's that many more tensors. It's just because of all the now gotta have like a negative mask in the image, or I don't know why is I don't know. I guess I don't understand really um, why we're getting out so many more tensors now.
We're
Was
only
it
getting
just
one.
simply because
We're only getting
what?
one more dimension, which is 2.
Oh, I see. Okay.
Yeah. So yeah, that is that's Unet. This is in Zeta, by the way. If you want to check it out. I'm writing the docs right now. So,
Okay. That's awesome.
yeah, so this is that's Unet. It's really important stuff. Really important. Now we gotta figure out the diffusion process. But because now you have the mask, right? How do you diffuse that? Like, what is the actual math for diffusion? So typically you would have this unit, then you would diffuse. You would add noise using Gaussian something Gaussian. Then you would diffuse. So then you would reshape the image to the image that you create. First you have a unit, then you diffuse, you add noise, and then you have the image you generate. Understand?
Yeah.
Yeah, so that's Unet.